All right, welcome everybody. Thank you so much for joining us today. My name is Cody. This will be our third installment of the HDR seminar series, and today I am joined with Juveena. So Juveena is going to be presenting on photonic crystal sensors for intelligent packaging, and she is from the Chem Eng department. So welcome, Juveena. I will hand it over to you now.
Okay, thank you, Cody. Hi all, I am Juveena and I am working under the supervision of Dr. Hao and Dr. Hua Chen. And today I would like to discuss about my research topic, photonic crystal sensor for intelligent packaging. Before I begin, I would like to acknowledge our country. So today I would like to introduce my topic, briefly discuss about the research background, literature review, research gap, research questions, and the experimental methodology I follow, some of my preliminary research and acknowledgements. So as I begin, I would like to talk to you about two real-life situations. The first is like we consume a lot of packed food every day, like meat, fish, etc. Sometimes we keep them in fridge, but we forget. Later we realize that it is expired. So usually we throw them into the bin. My question is, was that really spoiled? From my experience, I have cooked many such meat packets. Fortunately, I was never sick. Another situation is like sometimes we take these food packets like meat and cook them, and we feel some discomfort like some stomach ache or food poisoning. So my question is, does expiry dates help us to monitor food safety and food quality? When we look into recent reports, around 7.6 million tons of food is wasted in Australia, out of which 70% is edible. This causes emission of 17.3 million tons of CO2 emission, also wastes 2,600 gigaliters of water. So we need a solution other than expiry date. One such promising solution is intelligent packaging. So what is intelligent packaging is? It provides information about the quality of the food packet by monitoring the surrounding environment. For example, like when food starts spoiling, there will be change in temperature, pH. Sometimes some gases will be evolved, or there will be some solvents that will be released. For example, when when fish starts spoiling, it produces gases like trimethylamine, dimethylamine, ammonia, etc. So in intelligent packaging, such changes are measured and we get information about the quality of food or like signals. One such method used in intelligent packaging is dye-based colorimetric sensors. Some of examples of dye-based colorimetric sensors are listed here. These colorimetric sensors respond to the changes in temperature or evolution of gases, and they change color. But these kind of colorimetric sensors have certain limitations. As you can see, they all show very narrow range of color change. So it's not easy to be easily detected by our eyes. Also, they are easily decomposed by UV radiation. Also, they provide unreliable results due to the interference of stimuli like pH, temperature, etc. So we need sensors which are highly stable to UV radiation, which is highly sensitive and highly selective. One alternative material which can be used instead of dye-based sensors are photonic crystals. These are the nanomaterials which can control the propagation of light through them. So they are composed of periodically arranged dielectric materials of different refractive index. They exhibit photonic band gap, and which I'll discuss about it later. And when this photonic band gap is present in the visible region, they exhibit structural color. And photonic crystals are mainly classified into three types based on the morphology. They are one-dimensional photonic crystal, two-dimensional photonic crystal, and three-dimensional photonic crystal. So as we are dealing with colors, we should know some colors in nature. So colors in nature are mainly because of three reasons. One is because of pigments, and second is bioluminescence, and third is structural colors. So as you consider a leaf, and it contains a pigment called chlorophyll, and it absorbs red to blue light, and it transmits green light, because of which we can see green color. So the pigments are the reason for the color. When we observe these fireflies, there are some reactions taking place in their photophores, which results in their light. And in case of this butterfly, this is called a species called morpho species. And in this case, they have a reflective material arranged in a particular pattern. When light interacts with this reflective material, this brilliant color is produced. So structural colors are produced due to the interaction of light with this reflective material. So I would like to discuss some of the photonic crystal-like structures in nature. First one is morpho butterfly. Morpho butterfly, as you can see the SEM images, they have the pattern like one-dimensional photonic crystals. When they interact with light, we get this color. And in case of a peacock feather, they in the melanin rods from columnar structure, which are arranged in the form of two-dimensional photonic crystals, which when interact with light, we get this color, like this beautiful colors. And in magnification weevil and in nature opal stone, the arrangement is in the form of three-dimensional photonic crystals. So we prefer photonic crystals. The first reason is it has wide change of color. As you can see, in case of a dye-based colorimetric sensor, there is only narrow color change. But if we use photonic crystals, the color change is very visible, and it's very useful in case of a food sensor. So it has high selectivity, high sensitivity. Also, the synthesis method is called bottom up, so it is simple and cost effective. And we also can have a wide range of materials used to make photonic crystals. And also PCs respond to various solvents, vapor, temperature, electric field, and pH. So as I already discussed, in case of one-dimensional photonic crystals, the refractive index change is only in one direction. In two-dimensional photonic crystals, refractive index changes in two directions. And in three-dimensional photonic crystals, refractive index changes in three directions. We all know, many of us know about the semiconductors. In case of a semiconductor, they have an electronic band gap. These are certain range of frequencies in which the electron cannot transfer from valence band to conduction band. Similarly, in photonic crystals exhibit photonic band gap. There are certain range of frequencies at which light cannot propagate through the medium. Since light cannot propagate through the medium, it causes some interference or diffraction. Thus, the propagation of light through photonic crystal can be modulated. Based on this, photonic band gap are mainly related to two factors. One is the interplanar distance or thickness, and other is refractive index. So this can be determined using these equations. And when the external stimuli, in the presence of an external stimuli, there can be change in the effective refractive index or thickness. Thus, there will be change in the photonic band gap, which can be measured. So when we look into nature, we can see the materials used in natural photonic crystals have structure which are porous, and they can form well arranged structures. So based on this criteria, the materials used for PCs are metal organic frameworks and shape memory polymers and natural materials like silk. They are in the range nanometer, micrometers, and centimeters. In my project, I am using metal organic frameworks. So metal organic frameworks are the crystalline organic inorganic compounds. They are porous materials, and they can really form ordered structures, and they're composed of metal ions and organic ligands. Why I prefer metamorphs are because they have good pore size, geometry, and functional groups and large surface area. Due to these reasons, it can easily absorb light. And also the flexibility, it is really flexible, and it has good host-guest interaction because of these reasons. So the color change in MOF PC sensors are due to mainly two reasons. One is due to change in the effective refractive index. That is, when the MOF PC sensor absorbs some gas, there will be change in the refractive index, so there is change in color. Or else in other case, there will be change in the interplanar distance or thickness, that is change in lattice parameter, which leads to change in color. So some examples we can cite, is can see and observe in nature, are these beetles. In case of this beetle, the scales in the armor are mainly golden yellow color. But in the presence of when it absorbs water, there will be change in refractive index and the beetle becomes red in color. And in case of this fish, actually there's got some cyan color because of the interaction of the platelets with, because the platelets have some reflecting property. When the platelets interact with light, it causes interference and produce this color. But in the presence of stressful conditions, when water flows in, there will be inflow of water and distance between the platelets increases. That means increase in the thickness of the platelets, and therefore there is change in color. These are some examples we can observe in nature. Some other materials used in gas sensing are metal oxides, but they have limitations like poor selectivity, polymers, but they have also low selectivity and poor sensing performance. Carbon-based materials like graphene oxides have low selectivity sense and low sensing performance. The materials like ionic liquids, oxygen-free semiconductors, 2D materials, DNA, and biomaterials involves complicated synthesis in a commercial scale. So I don't prefer these materials. So when we observe the one-dimensional literature of the one-dimensional MOF PC sensors, there are no sensors to detect H2S or amines. Similarly, in the case of a two-dimensional MOF PC sensors, as well as in case of three-dimensional MOF PC sensors, there were no work reported H2S or amines. So this is a work where they use morph age for the to determine benzene vapor. And this is just to show for your information like how a MOS PV sensor work. When in the presence of benzene vapor, there is change in color, just to show you like how it works. And currently, the research gap involved is there are no MOF-PC sensors to detect amines or H2S, or limited MOF-PC sensors are only there to detect organic vapors. And also very few studies are there to present that shows the relation between the structure of MOF-PC sensors and their responsivity. So my task is to prepare MOF-PC sensors to selectively identify amines and H2S. Also, I want to study the effect of functional group and force size on the responsivity to analyte, and also how to observe how flexibility of the framework affects the responsivity to analyte. So my research methodology, what I experiment is like, first of all, I synthesize MOF and I'll characterize with SEM, IR, XRD, etc. Then I fabricate MOF PC sensors, again characterized mainly with SEM. Then I also do the sensing performance using reflectance spectrum. So for the method I follow is based on this literature. In a photo paper, I just drop a little of MOF solution and I cast it using this adjustable film applicator. So what I have to determine is the concentration of the MOF solution, which solvent to be used in MOF solution, and the solvent ratio, the thickness of the coating, and what temperature I do the casting. So currently, I am first year student. So like I just started. So this is after doing, this is like I got a pink color for my MOF. And these are the SEM images, and still I'm working on synthesis of MOF with better morphology. So, to conclude, intelligent packaging is a promising method to ensure food safety and food quality. MOF-based photonic crystal sensor is proposed to be a better alternative to current dye-based sensors, which can be used in intelligent packaging. So I would like to acknowledge my senior supervisor, Dr. Hao, and associate supervisor, Dr. Hua Cheng. And I thank my entire team for their support. I also thank RMIT University and RMIT's microscopic facility. I also thank my family, friends, and thank God, thank you all for the support.
Great job, Juveena. Now I think we can move to the Q&A section. So if anybody has a question, feel free to pop it into the chat or just raise your hand and I can give you the floor. While I wait for any, if there are any, Juveena, are you happy if I share your like maybe LinkedIn details or your email with everyone?
Yeah, fine. Yes.
Yeah, fine. Okay, wonderful. Does anyone have any questions? It's not looking like any. I saw you got some claps, so well done, Juveena. If there are no questions, I'd just like to thank you and everyone for your time. It was really good to end the year with something so wonderful. Hopefully we'll find something in December, but if there are no questions, I think there might be one just as I was about to turn off the recording. Nisansala says that this is a great initiative. Do you have any idea on how much of food waste can be reduced using this packaging type?
Sorry, I didn't get the question. I can't see.
Oh, the question's in the chat. So Nisansala says, do you have any idea on how much of food waste can be reduced using this packaging type?
Well, that's actually I don't have that broad idea, but this is a good solution as of now. That is what I feel. Uh, Actually, I cannot tell at this point like how much food waste can be reduced, but I propose it to be a good solution.
Does that answer your question, Nisansala? Yeah, awesome. Thank you so much, Juveena. Are there any more questions? All right, well, I would just like to thank you again for your wonderful presentation, and hopefully I will send you the link once this gets put online. All right, thank you.
Okay, thank you.
All right, have a great day, everybody.
Okay.
Bye.